Hi Bobcats! In this video we're going to take a look at some compounds that just plain don't follow the octet rule. There are sound reasons why some compounds just simply won't, but we still can draw valid Lewis dot structures for them. We just have to ignore the octet rule for them. The first big category of compounds that won't follow the octet rule are sometimes called electron deficient compounds, and that's probably going to be both of these first two bullet points. Beryllium and boron only bring 2 and 3 valence electrons to a compound, and they will form stable compounds that will have less than an octet, and there just simply aren't enough electrons to go around. So we're not going to try to make double bonds or anything like that with them to try to make octets. We're just going to leave them at less than an octet. And then there also are some species called radicals that will have an odd number of electrons, so there's no way that they can have an octet. They'll usually end up with something like 7 electrons. And then last but not least, there are going to be compounds whose central atom has more than an octet, sometimes 10 electrons, sometimes 12. So there will be some times where the best way to draw a structure is violating the octet rule. So these electron deficient compounds, if we're looking at very small atoms like beryllium and boron, there's beryllium and over here is boron, they just don't bring enough electrons to the party, and we're going to just let them be electron deficient. So for instance, over here with this beryllium hydride compound, hydrogen, each one of those hydrogens brings 1 valence electron and beryllium brings 2. So we only have a grand total of 4 electrons to work with in that compound. But even when we do have more electrons to work with, like in BCl3, boron is stable enough with 6 electrons instead of 8, and so we just leave the structure of BCl3 the way it's drawn here. We do not try to make a double bond with it. And then last but not least, we'll have species that are called radicals, and I don't really like the way that the software drew this radical. I'm going to just redraw this structure here. For NO, nitrogen brings 5 valence electrons, oxygen brings 6. So 5 plus 6 is 11. No matter how you slice it, you have an odd number of electrons, and so you're going to end up with a structure that looks something like that. I'm not sure why the structure drawing program moved that electron over the way that it did, but usually something like NO is drawn like here. So there will be compounds that are electron deficient. There just aren't enough electrons to put an octet on everybody. Beryllium and boron are the big clues for that. And then if you run into something that doesn't have an even number of electrons, you're going to have to violate the octet rule. Now going in the opposite direction, there is a group of compounds that are called expanded valence compounds. If an element is on the 3rd row of the periodic table or below, we can put more than an octet of electrons around it. Back when I was an undergraduate, the argument that was given for this was that if you're on the 3rd row of the periodic table, the atom can access its d orbitals, since 3d is the first shell, or the 3rd shell is the first shell that has a d subshell. I've seen arguments since then that are more in favor of size, that by the time you're on the 3rd row of the table, the central atom is simply big enough that it can physically accommodate having more than 8 electrons arranged around it. So I just want to draw a couple of structures here that illustrate this, SF6 and xenon tetrafluoride. So with sulfur hexafluoride, sulfur is a chalcogen. It's going to bring 6 valence electrons. There are 6 of the fluorines, which are a halogen, which brings 7 valence electrons. And so let's see, 6 times 7 is 42. plus another 6 is going to give us 48 valence electrons to work with for SF6. Sulfur will be the atom in the middle, and then we'll put 6 fluorine atoms around it. And if we're going to put an octet on each of these fluorines, we'll start with one bonding pair, and with this many atoms crammed in, I'm definitely drawing the bonding pairs as lines. So each one of these fluorines has one bonding pair and 3 lone pairs. And since there are 6 fluorine atoms, by the time we've drawn an octet on each one of these fluorines, we will have used 6 times 8, which is 48 electrons, and that's all of the valence electrons that we have to work with. So we don't have any leftovers to cram on the central atom. We don't have to start rearranging things to make double bonds. Just everybody has an octet. All of the fluorines have an octet, but that poor sulfur in the center actually has 12 electrons associated with it. Now for xenon tetrafluoride, since xenon is a noble gas, it's going to have 8 valence electrons, and there are 4 fluorines, which each bring 7 valence electrons. 7 times 8 is 28. I'm sorry, I said that wrong. 7 times 4 is 28, plus another 8 gives us 36 valence electrons to work with. Xenon will be our central atom because we have 1 of them, and then there are 4 of the fluorines. So I'll just draw the 4 fluorines, up, down, left, and right. And once again, I'm going to start putting in octets on the outside atoms. So I'll start with that bonding pair, and then complete the octet on the right-hand fluorine with lone pairs. Repeat that process for the other remaining fluorine atoms. Since there are 4 fluorines, by the time we've put an octet on each one of those, 4 times 8 is 32. So just putting octets on the outside fluorines uses up 32 of our 36 valence electrons. If we have leftovers, they go on the central atom. So we will cram in a lone pair of electrons here on xenon, and then maybe over here on the opposite side. It's generally a good idea when you put lone pairs on a central atom when it's a really crowded structure like this to circle them. That just kind of says, hey, this really is a lone pair on the central atom, as opposed to, oops, I erased and didn't quite erase every little dot. But once again, xenon here has, let's see, 2, 4, 6, 8, 10, 12. It has 12 electrons around it, clearly violating our octet rule, but that's just the way it is. So in this video, we were looking at exceptions to the octet rule. Beryllium and boron simply don't have enough electrons to usually have an octet, so they'll make electron deficient compounds. We run into that same issue with a compound like NO, which is only going to have an odd number of valence electrons, so there's no way that we can make an octet on everybody with an odd number of electrons. And then for those atoms that are on the 3rd row of the table or below, we can end up with more than an octet, and the 2 examples that we looked at actually had 12 electrons associated with them.